All right, let's talk about prediction. How much better can you get at guessing something if I give you just one little clue? Today, we're going to find a real solid number that answers that exact question.
Now, I gotta give credit where it's due. Everything we're covering today comes straight out of the fantastic Chapter 4 of Gianmarco Alberti's new book, From Data to Insights. Seriously, if you want to go deeper on this stuff, you should absolutely check out the full guide. It's a game changer.
So, at its heart, this is the question we're tackling. To make it fun, let's frame it as a prediction game. We're going to see just how much a single piece of information can boost our guessing power. So here's how we're going to break it down. First, we'll lay out the rules of our game. Then, we'll take a shot at guessing completely blind, just to see how many mistakes we make. After that, we'll introduce our clue, watch our errors hopefully plummet, and then we'll calculate the final score. And stick around, because at the end, we'll get into a few really fascinating quirks about this tool that you'll definitely want to know. The whole game we're about to play is built on this really elegant and simple idea called proportional reduction in error, or PRE for short. It sounds super technical, I know, but trust me, it's something you already do in your head all the time.
Think about it like this. If you look outside and see dark, angry clouds rolling in, your prediction that it's about to rain gets way better, right? Well, PRE just puts a number on that improvement. It measures exactly how much that clue, the dark clouds, reduces your error in predicting the outcome, the rain. It's that simple.
Okay, game on. For our first round, we need a baseline. Let's try to predict who survived the Titanic. The catch? We know absolutely nothing about the passengers. We are guessing completely and totally blind. All right, so here's our data for 139 passengers. Now, since we're guessing blind, our best strategy is to just pick the most common outcome. If you look at the total column, you can see that 809 people died while 500 survived. So the safest bet is to guess died for every single person. We'd be right 809 times, but we'd be wrong for the 500 people who actually survived. And that right there, that's our number. Those 500 incorrect guesses, that's our starting point, our baseline error. We're going to call it E1. So, burn this into your brain. Our starting error is 500. Okay, round 2. Let's play again, but this time we get a clue. For every passenger, we know their gender. How does that change our strategy?
We use the same logic, but now we apply it column by column. Let's start with the men. You see, there were 843 men in total. In that column, the biggest number is 682, the ones who died. So for every man, we guess died. That means we're wrong for the 161 who survived. Now, let's look at the 466 women. Here, the story flips completely. The bigger number is 339 for those who survived. So our best guess for all women is survived, which means we make 127 errors.
And just look at the difference that one clue made. Our total number of mistakes is now just 161 from the men plus 127 from the women. Our new total error, which we'll call E2, is only 288. We went from 500 mistakes all the way down to 288. That's a huge improvement. Okay, so we have our before score, E1, and our after score, E2. Now it is time to calculate Goodman-Kruskal's Lambda and find out exactly how much that clue really helped us. The formula looks simple because it is. We just figure out how many errors we got rid of, that's E1 minus E2, and then we divide that by the number of errors we started with, E1. It just gives us the proportion of the error that we eliminated. So let's plug in our numbers. Our original error, E1, was 500. Our new error with the clue, E2, was 288. So 500 minus 288 is 212. We eliminated 212 mistakes. Now we just divide that by our original error of 500, and we get our Lambda score, 0.424. And here it is, the big reveal. This is what that number means. We can now say with confidence that knowing a passenger's gender reduces our prediction error by a whopping 42.4%. That's the power of one little clue. But here's where it gets really, really cool. What if we flick the game around? What if we tried to predict a passenger's gender based on whether they survived? Is the predictive power the same in both directions? As it turns out, it's not a two-way street at all. When we predict survival from gender, we get that lambda of 0.424. But if you run the numbers the other way, predicting gender from survival, you get a lambda of 0.382. This tells us something fascinating. Gender is a slightly better predictor of survival than survival is of gender.
Lambda isn't symmetric, and that little difference can tell you a whole lot.
Now, for as powerful as Lambda is, it's not perfect. It's got a few quirks, let's call them, that you absolutely have to know about if you're going to use it wisely. First, and this is a big one, if you get a Lambda score of 0, it's tricky. It doesn't mean there's no relationship between your variables. It just means that for our very specific guessing strategy, the clue didn't help. This can happen when your data is really lopsided. Also, remember that predictive power isn't the same thing as statistical independence. And, of course, the golden rule of all statistics. A strong link does not, ever, prove that one thing causes the other. And that really brings us to the main takeaway. Lambda is a fantastic tool for measuring one very specific thing, how much a clue reduces your guessing error. It's a powerful lens, but like any lens, it brings one thing into sharp focus while leaving other things blurry. Knowing what your tools show you, and just as importantly, what they don't show you, that's the real key to finding insight.